Hello, here we are for part 4 of lecture 14 of CENG 4412 Steel and Concrete Design. In this part of the lecture, we're going to finish up with some of our theory for steel beam design, and in particular, we're going to discuss the theory and philosophy behind serviceability and deflection. And then we'll also finish up with some discussion of other failure modes for steel beams that we don't necessarily have time to get to this semester. So, deflections. Now, let's talk about how, at a broader view, how we design structures and how we design, at least in terms of beams and that sort of thing. So, design, broader view. Now, most of the time, and at least most of the time in this course, when we've designed things, we've been focused, or when we've done, when we have described design or we've described analysis, we have been talking about strength design. And so, of course, that's not always, so often that we consider that as, so sometimes when we're lazy, we refer to that as just design. But in reality, that is just one aspect of the design of structures. So really, we sort of have two big camps, two big philosophies. We have strength, and we have serviceability. We have strength and we have serviceability. So strength, this is going to be your LRFD or ASD design situation or philosophy. So this is where you have ASD, or as we use in this course, LRFD. You have load factors, you'll have resistance factors, all this sort of thing. And the whole idea is that, for example, if you're dealing with an axial load, or maybe you could have a, basically this is all based on strength, demand versus supply. This is strength, demand versus supply. And typically we're using, so we're going to use factors that increase the loads. So we're using factored loads and factored resistance. So these factored loads are going to magnify the effects of the load. So basically, when we first calculate a load, for example, dead weight, we will go around and say, okay, what is our best estimate, our best projection of what is the dead load for the structure? And then we'll add a multiplier, 1.2, 1.4, whatever that multiplier is, and we will increase that dead load. Same thing with live load. We'll do our best using the codes, relevant standards, etc., to estimate what the live load on the structure is actually going to be, and then we're going to add some on top of that as a margin of safety. And then in terms of design, in terms of strength, we'll do our best to estimate, okay, or to predict what is the strength of the structure, what kind of axial load we'll be able to take, what kind of moment we'll be able to take, that sort of thing. And then we reduce that, and we basically use a sort of demand versus supply approach that's saying, okay, well, we might have, for example, P ultimate is less than or equal to, maybe something like P ultimate is less than or equal to phi times P nominal, if you're dealing with something like a tension member. Or you might have M ultimate is less than or equal to phi M nominal, as we looked at previously. And in a more general case, at least in terms of the LRFD design, what we're doing here is our loads will tend to be the most critical loads we ever expect the structure to experience during its design life. So these are the usually major environmental loads. Things like if you're here in Houston, your major environmental load is typically going to be something like a really strong hurricane. If you're out in California, then that would be like the big earthquake or something like that, a major seismic event. Well, of course, we consider all sorts of different environmental loads, but your strength design often ends up being dominated by these major environmental effects. So your loads tend to be major environmental loads. But then your strength, in turn, will also be able to go really up to the limit. The strength, ultimately, when we do major strength design, ultimately all we really care about is, will the building completely fail, or will it fall over? Will it completely collapse? That sort of thing. We're talking about, will the building stay standing, if we're talking about a more broad level view here. Will the structure remain in one piece, effectively? Still stand, if you want to think of that in a more general case. So in other words, when we take, so for example, we have looked previously at, say, bending capacity, and we've considered the full plastic moment of a beam. Now, if you take a steel beam and you load it to the point where there is plastic bending from the top fiber all the way to the bottom, that beam has undergone major permanent deformations, and that thing is going to be bent all out of shape. We're basically loading up right to the point of it collapsing. It's really being overloaded. And so that's really not what we want to do. We really don't want to rely on that in terms of every day, so say day in, day out kind of stress, day in, day out kind of loads. But in your major environmental loading, so for example, if you're in an area with heavy earthquakes and there's a giant earthquake that rolls through, and all of the beams get bent out of shape, and they're clearly buckled and they're bent, and they just look horrible, and it's pretty obvious that you're gonna have, and the floors are cracked and the walls are cracked, and because they bent so much, the floors and walls and everything else are cracked, all the drywall's busted and everything else. Well, in terms of strength design, if this is a major event, like a major earthquake or something like that, that's only going to come along once a generation, once every 50 years, once every 100 years, I really don't care what the building looks like afterwards. I don't care if that building has to be condemned after this major earthquake, hurricane, etc. All I really care is that that anybody staying in that building, physically in the building at the time, doesn't die from the building falling in on their heads. Really, when we do strength design, that's what we tend to be doing. We tend to say, okay, well, for strength design, we're designing for the strongest loads this structure is ever going to experience. And in turn, we're going to let that thing go up right to the limit. We're going to say, okay, well, I don't care what happens to the building. I don't care if every brick falls off the wall. I don't care if the thing is just busted to hell and back. As long as it doesn't fall in and kill everyone inside, we really don't care. We can, buildings are cheap, lives are expensive, and lives have more value than buildings. I don't really care what happens to the building. We can build another one. Big deal. Obviously, that's expensive, but that's why you have insurance, et cetera, et cetera. Serviceability, though, is the opposite. So serviceability, this is not based on sort of will the structure still stand. Serviceability is more based on here is service. And what I mean by that is, or what we mean by serviceability is, will the structure perform adequately? Will the structure perform adequately under normal loadings? Under normal loading. Will it be adequate under normal loads? So here we're not doing any kind of factored loads. We are using only service loads, and service loads, of course, mean unfactored loads. Service loads, by definition, are unfactored loads. We're going to do our best to calculate the, say, dead load and live load, and we're not even going to multiply them by anything. We're just going to say, okay, well, on the average day-to-day type experience, what kind of live load will be on the building? What kind of dead load will be on the building? That sort of thing. We don't care about the crazy. Epic mega earthquake or the giant hurricane or anything like that. When we're talking about serviceability, we're talking about deflections. So we're talking not about strength, not about structural failure, but about deflections. So serviceability is all about deflections. So we're not asking if the structure will fail in terms of, now of course we can say something fails serviceability, but we're not asking if the structure will fall down. We're asking whether it will deflect too much, primarily. Will fall down, but whether it will deflect too much. Again, if it's going to be like a major environmental effect or a loading condition like a hurricane, etc., I really don't care how much it deflects. I mean, or I should say, but whether it deflects too much. But whether it deflects too much. So again, during a major environmental event like the big hurricane, big earthquake, etc., I don't care how much my building shakes. I don't care how much my building bends. I don't care how much my building sways. If there's a major earthquake, if there's a big hurricane, the whole idea with deflections is really more one of human comfort. We don't want to make if we have, if you have a normal building or something like that, just on a normal everyday type thing. Most people, if you're, say for example, if you're living in a tall condo tower or something, you don't want the building swaying back and forth on a normal day so much that you're getting seasick. That would be a deflection type limit, a serviceability type limit, and that actually can tend to govern a lot of the design of many tall buildings. Or if you're, say, there's like a regular steel frame building or something like that with maybe some metal decking floor or that kind of thing, as somebody walks across the floor, you don't want the floor to be so flexible that the floor kind of bounces up and down like a trampoline as they walk along. That would be perfectly safe. There would be no danger of the person falling through the floor when that happens. But and the same thing with a flexing building, the seasick, somebody being seasick up on the 50th floor of a tall condo tower or something. That's not going to cause the building to collapse, but in terms of normal habitability, people don't want to live in spaces like that. People don't want to work in places like that. People don't want to go to school or go have a factory or whatever it is the building or structure is being used for. People don't want to inhabit spaces that people like having the feeling that the building or structure that they're standing in is as well solid as a rock. The ideal deflection for human comfort would be 0. Now, of course, that's never going to be possible, but, people like their buildings stable. They get bothered if their buildings are vibrating too much or deflecting too much or bending too much. Even if I were trying to sell you a house and, as you walked along the floor bent up and down and vibrated in a slight breeze and everything else. Well, even if I told you that structurally it was perfectly sound, even if I got, a blue ribbon panel of a dozen of the most experienced, high-ranking structural engineers across the country, I could get a group of a dozen deans of engineering colleges or all sorts of people with all sorts of credentials, and they all signed off and said, we have analyzed this house and said it's never going to be a problem, and yes, it's deflecting like crazy, but hey, no problem, it's not going to fall over, it's perfectly safe, just live with it. Well, you're not going to be comfortable with that. Even if mathematically and in terms of physics and materials and everything else, even if the building itself or the structure is not going to physically fall over, if your house is literally bending in a slight breeze, even if it's perfectly strong, you don't want to live there just because it just bothers you too much. And also you have to start dealing with things like cracking drywall and cracking brick and all other sorts of problems. But anyway, but the opposite during an earthquake or a major seismic. So again, for buildings and things like that, for structures, we don't want them to bend too much under normal everyday load. We don't want them to twist too much. We don't want them to stretch or compress too much. We want to limit our deflections, but only in terms of everyday loading. For major seismic events, for major hurricanes, that sort of thing, serviceability is mostly about comfort, not about strength. So this is mainly a human comfort thing. This is about psychology. Primarily. And also damaging like certain materials, like drywall, that kind of thing. Affects with an A, not an E. Affects human comfort. And certain material damages, like drywall, things like that. Certain brittle materials, primarily. If the drywall is cracked in your house, that's not going to cause that's not going to cause your house to fall over, but it's something you don't want to deal with. It's gonna cause problems. So if your foundation is not stiff enough and your house bends too much under the loadings or under snow or under soils and shifting soils and things like that, all your drywall is going to crack, and you're not going to like that. You're going to have to get it fixed, and it's going to really bother you. But your house isn't going to be in any danger of falling over. That's a serviceability limit state. But then, so that's the kind of reasons that we tend to care about deflections. Now, for things like the opposite, though, for your major environmental loadings that dominate this side of the equation over here, the strength side, serviceability for deflections, for your major environmental effects, we don't really care about the deflections. Like if the building vibrates too much during an earthquake, whoop-de-doo. If the building vibrates or bends too much, if the floor bends too much during a hurricane, again, as long as it doesn't fall over, who cares? Most of the stuff is about like damage to, relatively cheap materials like drywall, brick, things like that, we can relatively easily replace as long as it doesn't fall in and kill anyone. We really don't care. Or a lot of it comes down to human comfort. So yes, nobody wants to inhabit a space if every single time on a normal everyday it's undergoing huge deflections. That tends to bother people. But if you're in a big earthquake, you're going to be bothered basically because you're in a big earthquake. It doesn't matter. It really doesn't matter whether the floor that you're in is vibrating by 1/2 inch or 1 inch. If you're in an earthquake, you're going to feel pretty bothered anyway. So, and it's such a rare event that we don't really need to worry about it. In terms of deflection anyway. So for major environmental loadings, we're concerned about strength, but for everyday loadings, we're concerned about serviceability. So here, and this is serviceability. With serviceability or deflections, we're going to use unfactored loads, and there you have it. So how do we calculate this though? So let's look at deflections. So deflections, though, just like strength design, do operate according to a supply and demand equation. So deflections / serviceability. Let's talk about deflections of steel beams. So deflections. So again, serviceability is with deflection, we are looking at serviceability limits. The serviceability limit state. And this is of course, because of this, we are using service loads, or another word for this would be unfactored loads. Service loads or unfactored loads. So here, and let's see. So how can we actually calculate this? Well, or let's look at the equation of demand versus supply. So instead of using a strength equation, we're going to use a deflection equation. And this is going to be the same kind of demand versus supply that we had before, except it's going to be, of course, slightly different. Well, actually, substantially different. We'll have delta actual must be less than or equal to delta allowable. So delta would be deflection. Oh, missed a delta there. Delta allowable. So we have some actual deflection and then some allowable deflection. And we just need ways of getting each of these. So let's first look at delta actual. And notice there's no factors on this. There are no factored loads here. Let's look at delta. Let's look at each of these. Let's break this down. Delta actual. The actual deflections present on the structure. How can you find this? Or present on a particular beam? Well, you could use things like, now in terms of most major, industry, structural engineering, when you actually do this out in the real world, in a non-academic setting, you tend to use, well, sometimes you'll use hand calculations, but what you tend to use more than anything nowadays, of course, is computer models. So you're going to use computer software, such as SAP, ETABS, etc. SAP, SAP, ETABS, maybe ANSYS, and many others. There are all sorts of structural engineering and mechanical engineering software packages out there that are capable of computing actual deflections. You can also use your theories that you learned in CENG 3325, and for those not familiar with our course numbering scheme here, that is our structural analysis, structural analysis 1. So all of the theories of structural analysis, all the theories there, they're talking about simple beam theory or working on things like virtual work or all the kinds of methods that you've learned previously in calculating deflections. And now, now in terms of some broader channel level things here, I am planning on putting a video series. I'm teaching this again in the spring, and in the spring I'm planning on putting together a 3325 video series that I'll be working on next semester. But so that'll have to wait till the spring. And of course, that's there. For simple things, for simple beams, relatively simple beams. I don't just mean simply supported, but it's, 1 or 2 spans, things like that, relatively simple things. The steel manual also has some very good tools that you can use, and you can find this on page 3-208, if I have my reference correct, in the 15th edition of the manual. Let's see, yes. And this is where you can find your shear, moment, and deflection tables, pre-calculated for, or not pre-calculated, but has formulas that have been pre-derived for a series of different types of beams. And simply supported, fixed, simply supported, fixed, fixed pin, all sorts of things. But you can use them, you could use that as well. For simple beams, you can use the table, and that is table 3-23, which has some pre-calculated shear and bending moment equations, essentially. And shear is basically what it has there. If you have this in front of you, you have, for each of these, you'll have maximum shears and also shear functions. You'll have reactions, and you'll have moment and also deflections. At least for many of them, you'll have deflections. So you can use that, and that again at least for the 15th edition of the manual, that is found on page 3-208. And then, so that's the delta actual. But then, what about the supply? Or sorry, that's the delta actual. And then, so basically, this is the. So that's basically the. Well, actually, in terms of demand versus supply. This would basically be your demand, and this would be your supply here. Because allowable, that's what you're allowing. That serves the same role as the allowable applied load, the max moment, that sort of thing. Your phi, m, n, that kind of thing. But then delta allowable here. Delta allowable. How do we get this? Well, really, this is usually given, at least for beams, in terms of ratios of beam length. So you'll have things like, very common to have things like L over 240, L over 360, etc. And do be very careful to use compatible units on this. It's very common for students in steel design or other courses, other undergraduate courses, to use. They'll get maybe a deflection in inches, and then they'll forget to turn the beam length into inches when they divide this out, etc., etc. But anyway, so watch your units. So these are 2 very common limit states. So, like, for example, if you had a beam that was, 20 feet long, if you had a beam that was 20 feet long, and your L over 360 was your governing state, well, you would have 20 over 360, so that would be 18. If this was 20 feet long over 360, so that would be, what would that be if I can math this late at night? That's no fun. 1 over 18th feet, and we'd have to convert that to inches. So that would be 0.67 inches if I math that correctly. Math is a verb. Great. But in terms of when you use each of these, though, and there are other limits as well, these can often be found in various building codes. And you can also find a version of the limits in the AISC Steel Manual. And it's found in the commentary, actually. It's on, it's section L2 in the commentary. And that's found on page, again, in the 15th edition of the manual, on page 16.1-478. What next? So looking at deflections. And that's the basic idea for deflections. Unlike concrete beams, when we talk about concrete beams, we'll have to look at deflections a lot more. But for steel beams, it's relatively simple. So, however, though, though it does seem relatively simple, often deflections actually govern, especially for steel structures. Deflections often do control. Actually do control. Because even if you have a a very reinforced member, that sort of thing, it's very easy on longer spans to get deflections lower than those limits. So surprisingly, often deflections do control. So it may not seem as as a big thing at first. We tend to think, at least when you're first learning how to do this, or first studying steel design as a student, often you focus on the strength design because that's the most obvious one. You see, okay, well, obviously I don't want my beam failing, I don't want my column failing. It makes all good sense. That strength would seemingly control. But when you actually get into the mathematics, often it turns out the deflection actually governs over strength in many cases. And we do have a few design aids that help us with the design of deflections. So when we were looking at the design for moment, often we wanted to have tables. It was very useful to have a table where the beams were sorted by the Z, the plastic section modulus. But there is actually, so because the equations for deflection are all in terms of EI, the E being the moment of inertia. So again, deflections are all in terms of EI, all proportional to this basically. And so E is not going to change. That's going to be your 29,000 KSI, your modulus of elasticity, if I can manage to talk properly. And I is your moment of inertia. However, so this is your geometry, that's the geometric factor that's going to, or the property of the shape that's going to determine your deflection capability. So it would be very useful if we had a table that was sorted by this, and we actually do. This is table 3-3 in the AISC steel manual, and what that has is W shapes sorted by IX. And that can be very useful for selecting a shape, because often what you can do is if you're having trouble with deflections, you can calculate what I you'll need, and then simply select the minimum lower lightest shape that will fulfill that requirement, sorted by IX, or the moment of inertia in the strong direction. And that really is the basic idea of deflections for steel beam design. And in terms of the theory, I will put together a follow-up video where I will run through an example, or I want to put together a video where I'll run through an example. But basically, in terms of theory, that's all I think I'm going to talk about in terms of steel beam design for this class. But do be aware that this is just an introductory course. We're only going through only going over this at a basic level. So there is a lot else we can learn. And there are actually other failure modes that we might want to consider. And I'll just briefly mention them here. So what other failure modes are present? Other failure modes. And you can read about these in the manual, and they each have their own section where describing how to calculate their capacity. Now, usually these don't govern, but depending on depending on the type of beam you have, they may. A first major one is the idea of flange local buckling. And this is where you just get local buckling in the flange. Fairly straightforward. Primarily in the compression flange. So if you have a W section, just generic W section, here, and you have a major amount of buckling just in the flange, like this, kind of like this, buckling out like here. And then basically this goes up here, you get major buckling in the flange. And this is found in this can be the equations and theory behind this, and you can read about it in the commentary as well. This is found in section J 10.1. Then we also have another one, would be web compression buckling. And this is basically where the web is, well, buckling, fairly straightforward. The web itself is failing under compression. Here. Oh, actually, no, never mind. I mislabeled this, sorry. That's flange local bending. Sorry about that, not buckling. Getting my notes all confused here. Flange local bending. And in this, you're applying a load, basically. you're applying some sort of load that's causing the flange itself to enter bending. So not bend, so it's not buckling. I misspoke. Sorry about that. It's you're applying a load, maybe like maybe you have a support here and a support here for some reason, and you're applying a load sufficient that this is actually putting the flange itself, not in terms of bending, a strong axis or something like that, but the actual flange is bending like a cantilevered beam. And depending on your loads, that can actually control design, depending on your loads and type of member. Then there's also compression buckling, web compression buckling. This is another one, and let's talk about this. So usually we don't load up W shapes like this. We tend to use, if we're using a W shape as a column or putting under compressive load, often, it's going to be loaded such that the load, as I've drawn here, as I've drawn the member here, the load would be going into the page. But what happens if I put one member on top of another one? Let's say I apply a downward load here. And and this would happen where you have one beam sitting on top of another one, or you have a floor slab resting on a beam, that sort of thing, a beam coming into a girder, anything like that. Now, yes, we've learned how to calculate shear and that kind of thing, and that's important, but the web here in this kind of case is acting like a column. And just like any column, there's going to be a certain limit beyond which it will just buckle. And so we'll actually have a limit state based upon that. And usually that's not going to control, but there may be some cases that it would. So it would just buckle out simply like that. And this is found in section J, J10.5. And then we also have another one we might consider is web side sway buckling. Web side sway buckling, or if I can manage to talk, web side sway buckling. And usually this is only going to occur if you have a very heavily braced compression flange, maybe like a fully braced compression flange, like say it's embedded within a large concrete slab, or it's maybe shear studs all the way along, that kind of thing. And if you try to keep putting load and load, more and more and more load on this thing, well, so let's say that this is a braced flange. Again, a braced compression flange. And then we're applying some load P to this thing. Well, even though the flange itself, the upper flange, even though the top flange, the compression flange, may not be able to buckle, and because it's continuously braced, that doesn't mean the entire thing is braced. So maybe just the lower flange and the web will buckle out something like this. And that is the idea of web side sway buckling. It's called side sway buckling because even though the upper flange is rooted firmly in place, the bottom flange is free to buckle or sway to the side. And you can read about this in section J10.4. And so my point here is not to say that these are always going to control, or to even say that these four are the limits of steel design. They're definitely not. They're even just the limits of steel beam design. There are many, many, many types of failure modes that we have learned, basically in terms of experience and from studying failed buildings, from laboratory experiments and all sorts of things. There are many things over the last generation or two, several generations actually, many decades, that structural engineers have learned how steel behaves as a material. And so, and the code basically encapsulates many of these types of failure modes. So what I'm teaching you in this course is just the very, very basics. And hopefully when you learned, basically my hope is after going through this course, you'll have learned enough that you can teach yourself most of the rest of the things if you really need to learn about them. So if you've grown comfortable working through the equations of, say, chapter F, the main equations of chapter F, really, at that point, you know how the steel manual works. You know the basics of the idea. You know the basics of how to cite it, how to work with it, etc. And at that point, you're probably comfortable doing research on your own to find and to read and learn about other failure modes. But anyway, so today I just wanted to finish up with, for this portion of the lecture, I just wanted to finish up with deflections, and also finish up some final theory on steel beam design. All right, that'll do it for this portion of the lecture, and I'll continue on shortly. And as always, thank you.